My name is Michael Roller. I work in the MServe division, and today I'm excited to talk to everyone about edge computing and its impact within information technology. Hopefully, I will be able to keep you all on the edge of your seats throughout the talk, but I'll try my best not to make too many edgy jokes this talk. In the rapidly evolving digital age, there are several challenges that traditional computing paradigms struggle to address adequately. This has created a need in the industry for edge computing. One of these challenges is that data generated around the globe is increasing exponentially with time. The sheer volume of data can overwhelm centralized architectural designs, leading to slow response times and network congestion. Another concern is the increasing concern for privacy and data security. Transmitting sensitive information over long distances leaves it vulnerable for interception and eavesdropping. On top of that, many industries such as manufacturing, healthcare, and transportation require instant decision-making capabilities and close to real-time processing of data for their daily operations. Edge computing emerges as a promising solution to these challenges by enabling data processing and analytics to perform closer to the source of data generation, cutting out lengthy transmission times. This reduces latency, enhances privacy, and improves overall system efficiency. Basically, what it all boils down to is edge computing is fast. So if centralized computing were to talk like this, then edge computing would talk like this. But what exactly is edge computing? It can be a bit of a gray area, but in my opinion, edge computing is when people use Microsoft Edge to browse the internet. But you should probably listen to the professionals instead. According to IBM, edge computing is defined as placing distributed workloads as close as possible to where the data is being generated. Did you know that it would take around 130 milliseconds for something to travel around the globe at the speed of light? That is some pretty high ping. Since data cannot be transmitted faster than this universal speed limit, distance is the primary source of latency in modern networks. This is what edge computing aims to resolve. So instead of thinking where data is being stored, edge computing forces us to think about where the data is being generated. It's rarely generated by humans and the equipment that they use. The equipment that generates this data can be defined as edge devices. These devices are built to perform some sort of function and just happen to have compute power. You can think of smart cameras, IoT devices, processors on a car, mobile phones, etc. And in conjunction with these edge devices, edge servers can be defined as a piece of IT equipment that can be used for computing IT workloads. These are the physical servers that need to be located as close to the edge devices as possible. They can handle multiple simultaneous edge device connections at the same time, which is why they often employ Kubernetes for elastic scaling and high availability. The edge servers are located before what is known as the network's edge, meaning that data will not have to be transmitted long distances to central cloud data centers for processing. There has long been the promise of combining 5G technology with edge computing to achieve sub-1 millisecond latency. That's 1/1000th of a second, or about the length of a typical camera flash. Although this would be the best case scenario under ideal conditions, in a more general sense, IEEE notes that the introduction of edge computing typically improves cloud access latency by about 30%. So I'm just going to take you through a few examples where edge computing proves itself to be quite useful. So for industrial IoT, factories can use it to monitor equipment in real time, which predicts maintenance and downtime faster and more reliably. Smart algorithms are being developed for task offloading schemes that IoT or mobile devices can use with mobile edge computing to optimize battery life against latency. This allows a device to probe conditions in its environment, decide whether to process a task locally or offload it to a nearby edge server. Having distributed edge servers located around a smart city could power traffic management, environmental monitoring, and public safety systems. This could also provide autonomous vehicles with real-time traffic updates and give them the option to offload some of their sensor data to be processed externally. I'm sure at this point, a lot of you are imagining a world where 5G-powered AI seamlessly flies your self-driving car in the clouds, processing data at lightning speeds. Pure bliss, right? Although edge computing has a lot of buzz around it, it promises a lot of things. The reality is that managing it itself can leave you a bit flushed. Because computing workloads are so diverse in many different industries, edge computing solutions will all be different and require careful management techniques to distribute these workloads at scale without requiring administrators to go out and assign these workloads to individual devices. These edge devices typically exist outside of IT data centers and don't have the protection that is typically associated with them. There's also a need to ensure that workloads don't get tampered with when they are deployed to these devices and have methods to detect this and remediate it. Luckily, there are some commercial solutions that make it a bit easier to manage workloads at the edge. So most major cloud vendors offer content delivery networks such as Amazon CloudFront. These are used for caching static files at the edge to reduce having to request them from a centralized server. However, this can be quite limited because it's restricted to static files and not dynamic files that require processing. So instead of just caching data at the edge, there are also some solutions to bringing the actual servers closer to the consumers as well. This usually involves serverless functions that are lightweight, stateless operations. And some examples of this is Lambda at Edge, Cloudflare Workers, and Vercel. Although there are many benefits and use cases for edge computing, it's not always the solution to slow response times. It needs to be used correctly to unlock its full potential. It does not help if you have workloads located at the edge in Australia, if those functions then need to fetch data from a database located in Ireland. In this case, it would be better to have a central server located close to your database to serve back the responses. In this case, edge computing would actually be slower than having a single server. One way to counteract this, however, would be to distribute your database around the globe using something like Cassandra or Redis caches. You could also cache server responses, so the full round trip doesn't have to happen on subsequent requests. And luckily, there are some modern web application frameworks, such as Next.js, which you can use in conjunction with something like Vercel, that allow you to opt in only some API routes for edge computing, as well as response caching. So this allows developers to opt in more lightweight routes for edge computing while leaving some to run on a central server. Many companies are employing this hybrid cloud strategy where critical processing happens at the edge and more extensive analytics or storage happens in the cloud. So to wrap everything up, edge computing is a powerful solution to some of the most pressing challenges in today's digital world. While it promises lightning-fast processing, real-time decision-making, and enhanced privacy, it's essential to remember that implementing it requires careful planning and management. As we've seen, edge computing isn't a one-size-fits-all solution. It must be tailored to the specific needs of each application. By striking the right balance between edge and cloud, we can unlock its full potential and drive innovation forward. Thank you for joining me today. And remember, while edge computing is complex, it's all about bringing the power of computation closer to where the action happens. Just try not to put too many servers in the bathroom.